Hello friends, you are watching ERUDIRE PLUS, the professional CAD/CAM solution provider. Let's get started.
Hello friends, today I'll show CFD flow simulation and parametric study of a fluid through this globe valve. In this analysis, the most important part is the controlling these flow particles, and we can control the pressure, temperature, velocity, etc. with this wheel. The wheel can rotate clockwise or anti-clockwise direction. As the wheel is rotating in a clockwise direction, it will come down and it will restrict the movement of flow particles, and whenever it will move in the anti-clockwise direction, it will remove the restriction of flow particles. For better understanding, let us cut this valve along a specific plane. Let us cut it along front plane. So you can see that the plunger is this one. The plunger can move up and down with the rotation of this wheel, and for this wheel we have provided screw connection. That means with a specific pitch it can move up and down. In this connection we have provided a pitch of 1 mm. That means whenever the wheel is rotating by one rotation, it will come down 1 mm, right? Even the movement of this plunger is completely restricted. It can move from this location to that location. That means its motion is completely restricted for a specific length, and the diameter of this pipe is actually 35 mm. Similarly, the plunger is also restricted to move from this location to that location with a specific rotation of this wheel. We will start this simulation from the assembly itself, and after normal simulation we will go for some kind of parametric study and see at specific rotations what are the different parameters like flow particles, pressure, temperature, velocity, etc. and the exit surface. By the same time, we'll do something else, like throughout this passage from extreme left hand to right hand, using XY plot, we'll find out pressure, temperature, velocity, etc. at different locations. Okay, so let us start this one from the assembly. We'll start from assembly. In the desktop, we have created this folder already. Both the parts we have selected. This is the globe valve, and this is the wheel part. To assemble these things, in the assembly, first of all we have to provide the axis of these two should be collinear. So you can see the axis from here. So we can select both the axis and we can mate it. Mate and select the axis. Done. Next one, you have to provide a specific distance for these two different components, right? Now we want to provide a restricted motion of this plunger in order to have restricted motion of these flow particles inside this pipe. So for that, what we'll do is we'll select the components, this part and the bottom part of this mat. And from the advanced mats, we will select the maximum and minimum distance in between them. You can select advanced mats, and the distance in between them should be 35 mm to 0 mm. Let us accept this one with green check. Done. Now you can see the sectional view and check the motion of these components. See, it is coming down up to the bottom part of this pipe, and its maximum distance is this much only. You can see here we have provided a restricted motion of this plunger. It can come down up to this position maximum. When it is coming down up to this position, it will restrict the motion of flow particles from this pipe, and with the counterclockwise motion of this wheel, it will go up, and during that time all the fluid particles will be flowing through this passage. And to provide a restriction of these flow particles, we can rotate this wheel. Now we have provided the restricted motion of this plunger. Next to that, we have to provide a screw connection in between these components, and we want to provide a pitch of 1 mm. That means for complete rotation of this wheel, it will move down 1 mm, right? So next to that, we have to provide screw connection in between these components. Okay, so met Before that, we want to see the complete view of the model. Next, we want to provide screw connection in between these components. Met, and from mechanical mets, you can select screw, and here two options are available, that is revolution per millimeter and distance per revolutions. Let us select the first one, that means revolution of this wheel will be taken as the input parameter. With one revolution, it can move through a vertical distance of 1 millimeter. That means we are providing a pitch of 1 millimeter. Okay, and to provide a screw connection, we have to select the two mating surfaces. Let us select this one and that one. It is done. Green check. Now let us see the motion of this wheel. Green check, accepted. Now we'll cut this valve across front plane and see the motion of the wheel. Okay. Now see, as I told that whenever the wheel is rotating in a clockwise direction, the plunger will come down and it will restrict the motion of the flow particles. Let us see, whenever it is moving in a clockwise direction, we can see the plunger is coming down. With one rotation, it is moving down 1 millimeter, right? Let us see. The plunger is coming down. We can do this one manually, we can do automatically also, right? See, at this location, let us move down more. With clockwise rotation of this wheel, the plunger will come down more. Okay, this is the position. Now what can I do is, at this specific location, we can start one simulation, and in the parametric study, we will have a different rotation of this wheel, and with the different rotation of the wheels, we will see the different goals like pressure, temperature, velocity at the exit location. Okay, so we can start this one. Let us have a complete view of the model. And also one thing we can do, like to have a XY plot, we have to get a straight line from the front plane. We can select the front plane and draw one straight line, normal to. Let's start one sketch with a 3D sketch. Let's start a straight line. From this location to the exit end. Done. Green check. Next one, we have to go for analysis. So before analysis, we'll save this part. Let us save this one by the name of glove valve assembly. Next to that, we have to create a closed geometry, and for creating the closed geometry, we have to provide leads at the entry and exit locations, and that can be started with the flow simulation itself. Tools, and we want to provide leads at the entry and exit locations. Create leads. Let us select the surfaces to provide leads. One lead is made. Now the exit lead to be prepared. Exit lead, select. Both the leads have been made. Now for better understanding of these flow particles, we can make this model transparent. Let us select these models and make it transparent. Model is transparent. Now we can see the flow particles and pressure, temperature, etc. very easily. Okay. And for applying boundary conditions and etc., we have to cut this model along a specific plane. First of all, flow simulation environment should be created, and that can be done using wizard itself. So wizard, and we are keeping the name of the project as project 1. Next, the unit system will follow as SI system, and temperature will be taken in degree centigrade. Next, it will be an internal analysis, and we are considering gravity. Direction of gravity will be along y direction, so along y it will be minus 9.81 meter per second square, and along z direction it will be 0. Next, liquid, it will be water as the default liquid. Next, thermodynamic parameters, we are considering temperature to be 20 degrees centigrade and pressure should be 101,325 Pascal. Let us finish this. This is the computational domain. We can see this is very small one. We can edit this part, and while editing this part we should ascertain that all the parts of these components should be inside this domain. So we can make the domain a little bit bigger. So this is the computational domain. It is ready. Next we can hide this domain and go for different boundary conditions. And always it is suggested to have a segmented view of this model for providing boundary conditions. So we can cut it along front plane and provide boundary conditions at specific locations. Initially we have to provide water from the entry location at a specific rate. Let us provide velocity of water from the entry location at 60 meter per second. Green check. And another boundary condition is required. Atmospheric pressure at the exit location to be provided. Select that location and it will be atmospheric pressure or environmental pressure. Green check. Both the boundary conditions have been applied properly. Next one, we have to select some goals. We can have a lot of goals, but in our analysis our main aim should be to have pressure, temperature, etc. at the exit location. So we can select some surface goals. Insert surface goals. We want to have average pressure, temperature and velocity at the exit location. Select. Green check. Now we can run this one and see the simulation results. Let us run it. We are starting with a new calculation. Run. Solver window has already started iterations. Let us see. Mesh refining is going on. Solver is finished. We can see the results from here. We have two different goals, that means pressure and temperature at the exit location. You can see after 109 numbers of iterations, average total pressure at the exit location is 1.93 into 10 to the power 6 Pascal, that means 1.93 megapascal. And average velocity, we can have a little increase in average velocity. Initial velocity was 60 meter per second, but at the exit location velocity is 60.06 meter per second. Right, now you can see the results from the cut plots and from goal plots also. At the same time, you want to see all the relevant results using XY plots. Close it. First of all, you want to see cut plots. Insert. Let us see velocity. We want to see in the form of contours and vectors. Let us see these things. This is the velocity plot across front plane. You can see at the location where the plunger is coming down, at that location velocity is high. It is in the range of 102.66 meter per second, and as it is passing at the exit location, its velocity again increasing. You can see the velocity at the exit location is equal to in the range of 60 to 70 meter per second, and at the entry location it is 60 meter per second. You can see the pressure also. Here again pressure at the entry location is 189,0887.58 Pascal, and at the exit location it is less. You can see the color, it is in the range of 157,224.11 Pascal. So we can see that there is some reduction in pressure at the exit location. Right, let us play these things in the form of an animation. Let us clear and hide this. This is not our aim. Our aim is to see the parametric study with the rotation of this wheel. At different numbers of rotation of this wheel, the plunger will restrict the motion of flow particles and we will get different output parameters at the exit locations. Okay, next one we want to see the dynamics of flow particles. Flow trajectories. Insert. And instead of 20 numbers we want to see 100 numbers, and instead of pipes we want to see in the form of arrows only. Let us select the locations, entry and exit location. This is the entry, and we will select the exit location also. Both the locations selected. Green check. Now the particle study is going on. Now see how the particles are moving from extreme left to right end. It will be better to see this dynamics of flow particles in the form of an animation. First, let us clear and hide this part and we'll see the animations. Let's play. Better to see from the front plane. Now with the rotation of this wheel, the plunger will come down, and at a different location of this plunger, we can have different output goals at the exit location, right? With the parametric study, we'll go for these things next to that. Okay, let us clear and hide this part. And we want to see the goal plots. We have already seen the goal plots from the solver window. In this case, we want to see in the form of graphs. So select all the goals and show. These results we have already seen. So we want to see these things in the form of a graph. History. We can see pressure has come down actually. And average velocity also, it has come down. Let us clear these things. Next, we want to go for some kind of parametric study. And in this parametric study, our input variable will be the rotation of this wheel. And with different rotation of this wheel, we'll get different output parameters at the exit location. Okay, so let us start a new parametric study from solve. New parametric study. And here in this case, we want to have design of experiments and optimization. And for this parametric study and optimization, we have to depend on input variables, and that input variable may come from the boundary conditions or from the geometry. In this parametric study, we are considering geometry, or you can say the rotation of the wheel as the input variable, so that can be selected from the geometry itself, right? Select the geometry, and we can select the geometry from the original assembly conditions. And from the assembly condition, we want to select the assembly of the screw. That means we want to provide rotation of the wheel as the input variable. It is selected. Rotation of the wheel is selected as the input variable. Green check. And here in this case, you can see rotation number equal to 1. We have to vary this range from 1 to 35. Because maximum diameter of this passage is actually 35 mm, and we want to provide a rotation of the wheel from 0 to 35. That means at 0 rotation, the passage will be completely free, and when the rotation is 35, it will be completely blocked. Okay, so green check. In this case, we know that we have provided a pitch of 1 mm. That means 35 rotation means it will move a distance of 35 mm. Okay, we have specified a rotation of 0 to 35. Next to that, you have to select output parameters. From the output parameters, you have to select the goals. We have only 2 goals, both of them selected. Next one, we have to select the scenario. Here in this case, we have 5 numbers of experiments. Let us create these experiments. That means we can provide different rotations of the wheels, and with different rotations of the wheels, we can have different output goals. These values are automatically generated. We can vary these things. Let us vary these rotations. We can make this one as 30. This one may be 25. This one may be 20. So we have got 5 different numbers of rotations of the wheel. At 5 different rotations of the wheels, we will get different output goals. Okay, let us run this one. Iterations have already been started. The solver is finished. We can see the results from the design of experiments and optimization. We can see that there is not that much of changes of pressure and velocity, and it is clearly evident that when the rotation is 0, in that case we can have maximum velocity of flow particles at the exit locations, right? Now all these things actually depend on the geometry. From these results, it is clearly visible that when the rotation is 0, that means when the passage is completely free, in that case velocity at the exit location is maximum. It is 60.056 meter per second. And when the rotation is 35 numbers, in that case the object will be completely closed. Here in this case, you can see velocity of flow particles is less. It doesn't mean that it is completely closed. When it is coming down to 35 millimeter, the path is not completely closed. It is showing that some velocity is there. I have some doubt with the results obtained from the last simulation data. That means when the plunger is coming down at the lowest position, can recheck this with a new simulation. So we can start a new simulation with the latest position of the plunger. Starting a new project as project 3, and temperature we can replace as degree centigrade. It will be an internal analysis, and we're considering only gravity. The direction of gravity will be y, so along y-axis it will be minus 9.81 meter per second square, and along z component it will be 0. Next, a liquid will consider water only as the main default liquid. Next, default wall thermal conditions and roughness will be considering. And next, this is the computational domain. Now apply our boundary conditions. Before that, you have to hide this domain. Insert boundary conditions. You have to apply the similar boundary conditions what we applied before with the present location of the plunger. So initially it will be forcing liquid with an inner velocity of 60 meter per second from the extreme left hand side position. Thermodynamic parameters, temperature will be 20 degrees centigrade. Let us select the location for this inlet velocity. Green check. Now we have to define another boundary conditions. That means atmospheric pressure at the exit location, and the temperature will be 20 degrees centigrade. Let us select the exit location. Selected. Green check. Both the boundary conditions have been applied. Now we can see the goals. We have to define two surface goals. Insert surface goal. We have to have average pressure and velocity at the exit position. Let us select that location. Selected. Green check. Now we can run this study and see the dynamics of flow particles. Whether it is matching our previous results or not, that can be checked. So we can run it with the new calculation. Iterations have already started. Mesh refining and capturing is going on. Let the iterations move on. Whenever it is finished, we'll see the dynamics of flow particles to compare these results with the previous data obtained from Parametric Study. The solver is finished. Now let us see the results. We have to select both the goals. You can see the results, like velocity at the extreme right hand position is in the range of 2.1 to 10 to the minus 5. It is very less, and also average temperature of fluid is 20 degrees centigrade, which is not varying that much. Let us see the dynamics of flow particles. Close it, and when you see the flow trajectories, insert flow trajectories. Instead of 20 numbers, we want to make it 100 numbers, and instead of pipes, we want to see in the form of arrows only. Let us select that location for these flow particles. It is coming from extreme left and going to the extreme right position. Green check. Particle study is running, and you can see at this location no flow is occurring actually throughout this pipe. At the extreme right position, you can see some kind of backflow is occurring, right? That's why the data we got, because of the backflow of these flow particles. Okay, this is quite abnormal as per our expectation. Further, we can investigate these results, and that will be done with a different video. Okay, so next to that, we want to go for some kind of XY plots. XY plots. Insert. Let us select all the parameters. We want to see density, pressure, temperature, etc. And for better accuracy, you can make the resolution a little bit higher. Let us select the line from the geometry itself. This is the line. So along that line, we want to have pressure, temperature, etc. Green check. Let us show all the plots. It is showing all the XY plots like density, pressure, temperature, etc. You can see from these XY plots From the density analysis, you can see that initially density was less, and at the location where the plunger is coming down, at that location the density of water particles is more. It is in the range of 997.75 kg per meter cube, and initial density was, it is in the range of 997.57 kg per meter cube. Similarly, you can see pressure, temperature, etc. Even other things like temperature of fluid, velocity x component, y component, z component. We can see other things like vorticity, relative pressure, and again you can see bottleneck number and shortcut numbers. Even you can see turbulence intensity and turbulence lengths, turbulent dissipation and turbulent energy. All these things you can see from these XY plots. Okay, good, check. Now in this study, what we got, we control the rotation of this wheel, and the rotation of the wheel actually control the flow particles. As the particles were moving from left to right, and at the exit location we've got some pressure, temperature, velocity, etc., and those output variables were controlled by the rotation of this wheel. Okay, this is all about today's analysis. If you like this video, please subscribe and share, and if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.